We're going to hear from Carlos Babativa Rodriguez. So Carlos is a project officer at DPIRD, Western Australia, and he's got a background in computer science and mechatronic and software engineering, which is fantastic. So Carlos has been working in crop protection and invasive species since 2017 and working on implementing systems for capturing and analysing imagery and other data that's integrated with weather patterns, GIS and workflows and other technologies. So this work has included in-crop and in-harvester pest monitoring, the use of microwaves for managing seed beds and bulbs, and the compilation of AI-ready data sets, which amongst other things have been used to detect skeleton weed and rubber vine drones. And so Carlos is going to talk to us about these AI-ready data sets and proof of concept weed detection using drones on skeleton weed and rubber vine. So Carlos, over to you, please. Oh, and you're on mute, mate.
Thanks, Justin, for the introduction. And yeah, I'm just sharing my screen now so you can see. Can you all see my slides?
Yes, thanks. That looks great. Thanks, Carlos.
Perfect, thank you. So yeah, so I'm going to talk about mainly the AI ready data sets that we're preparing for detection of weeds in the landscape. This started for skeleton weed in the wheat belt, and it has now go across to rubber vine. And I'm also going to present a little insight into tap into some work that we've been starting to do for innovative invasive surveillance using pollen and eDNA, two separate components, but that also fit into one another. So basically, skeleton weed has been under eradication in WA for a large number of years, and in 2020, the last review has revealed that more surveillance needs to be done to be able to properly delimit the extent of the weed, and to be able to utilize better the budget. And the cost benefit of the program is 8.6 million over the next 30 years. So, and this is the current extent of skeleton weed. It's being contained at the moment, or the spread of it is being contained at the moment. But more efficient surveillance is going to help a lot with the extirpation of the weed in the areas where it's not widespread. So the typical motivation for eradicating or for using drones for weed detection is it's almost like a holy grail, isn't it? So the expectation is that you will cover vast areas. There's no movement restriction. There's sharp equal view of the landscape, and you can spot every last weed. But the reality is that there are several constraints in terms of the biology of the plants. Sometimes they only flower for a certain time of day or for a certain time of the year. And the flight and capture parameters do limit your capacity to be able to cover the area that you need to cover during the time of the day that you need to fly. So basically, what AI, how AI works for drone imagery is it does require each image to be 1 megapixel during training. So the imagery has to be tiled up into smaller sections so that it can be fed into the model. And this imagery will be having annotated data. That is whether it is presence or absence of weeds in particular tiles, or weeds marked with squares, or with tight boundaries around them. Each method obviously takes more or less effort, but also it translates into more or less accuracy. We split the data set into a test data set that is set aside for testing later, and the training and validation data remaining is used then. So we put the 80% of training data through the model. That gets tested on a validation data set, and that gets repeated several times, usually 300, 400 times, and the errors start coming down, and then the last set of data that was set aside is tested so that we can get metrics. We can then track the performance of the models. So that's what we refer to as AI-ready datasets that are labeled, that are cut into tiles, and then split into train and test validation datasets. But how do we get there? So it's very important to know where your weeds are and where your images are. So we basically map the footprint of each image, and we map the footprint of each of the plants or clusters of plants that are there. And then we overlay the ground truth data and imagery, and the ground and the aerial imagery. So 2 case studies that we have been working on, skeleton weed and rubber vine. We take a bottom-up approach where we start designing the parameters of the flight based on the biology of the plant. So for rubber vine, we use the flowers that are on top of the canopies. For skeleton weed, we use the stems mainly that are at the ground level. So ground sampling distance or target sampling distance, that will be the factor that we go off to start planning our flights. Skeleton weed has 2 to 4 millimeters branches, and they're very, very, very thin. And the flowers only flash in the morning, so we can rely on the flowers to detect the skeleton weed. As opposed to rubber vine, where it does have flowers, they're very big, and we can rely on the flowers to detect them. The smallest adequate size for an AI to detect small objects is about 2 to 8 pixels aside, and if we use something that's typical in the agriculture sector, something like 40 millimeters per pixel, we're gonna completely miss the plants. So we need to go with much finer ground sampling distance, 2.7 millimeters per pixel we use for skeleton weed. And for rubber vine, we do use 5 millimeters per pixel. That covers about 6 centimeters would become 12 pixels across the flower. So that's a very good representation of the plant. So for ground truthing, again, we can use for rubber vine, we can use coarse accuracy location of the plants, because the bigger plants we can sort of only know exactly where each of them are. For skeleton weed, we do use an RTK system that gives us more centimeter precision of the position of each plant, so that then we can locate each of the plants in there and put a square around it. We use a GIS processing method that then allows us to ignore everything that hasn't been ground truthed, and everything that has been ground truthed it will be included in the data set. And if there are overlapping images, the tiles are not going to be repeated they're not going to be used twice, or it deduplicates basically the imagery. And it also allows us to use visibility scores of the plants. If there are plants that are not visible, that are going to be detrimental for the model, we can also remove them in this process. And then the last step is to go and validate the detections that the model provides us. And this map on the left-hand side shows us plants that have been mapped in swords. Then we can go and have a look at those specific images where the swords have been mapped by a ground officer, by a field officer, and we can run the detection on them and validate the detection to put more data into the model. So this is where it's really important to have humans in the loop, so subject matter experts, biosecurity field officers that are experts in identifying the plants from lookalikes into the system. We use Label Studio. It's an open source software that's very flexible for anyone to use. And we basically train the model. perform some detections, and then we have a validation guidelines for the field officers that use the infrastructure of DPIRD to both locate the plants in the ground with their tablets, and also go back into the office and have a look at what detections we're going to reutilize in the data set to keep on feeding the model either false negatives, plants that have been missed by detection models, or false positives that have high confidence. So this is the main part that I wanted you to be interested in, is using the human in the loop. Currently, we are detecting skeleton weed plants. Even though they're very thin, we can detect them in the landscape. And this photo on the right, it's just one photo of rubber vine that was taken from a helicopter. It was using a different camera from a different height. And even then, the initial model was able to pick up all of the flowers that are visible to the human eye. That was a very satisfactory result. So we're still building the models for it, and we have started tracking the progress of each of the models. So we do want to recall that sensitivity metric, drive it higher and higher upwards. And the only thing I wanted to present about pollen and eDNA, there are initiatives that we have started looking into. Also, that will be working on for surveillance of species in the bigger landscape. So the wheat belt is a reasonably big area, up in Kimberley, reasonably big areas where we can't always go and have a look at plants ourselves. So active surveillance is very challenging. So passive surveillance methods like pollen traps, we've started to look at. So this is actually an automated pollen trap that our colleagues in Grains have developed. It has a carousel that changes every couple of days. And you can have 8 different slides with glue to capture pollen, and it's being used for monitoring rust spores in the wheat belt. So we reutilize them in summer when they're not utilizing them. We reutilize them to monitor for skeleton weed, and this is the reference imagery of what the skeleton weed pollen would look like under scanning electron microscopy, and we have some imagery that we have captured by scanning the slides, and both using pollen and the pappus of the seed of skeleton weed seed, we can get some passive surveillance occurring. We have had challenges. So when we use the glue that is being used for rust identification, it does it comes up with too much noise for the scanned slides to be able to be useful for training an AI. So we have been exploring alternatives like positively charged slides, which don't require any glue. They simply attach to the surface of the slide by the electrostatic of the slide. The other surveillance that we have started looking into, and CSIRO is doing some sensitivity tests for the primers that are being developed for skeleton weed, is eDNA surveillance. So this is an oversimplified view of what the system would look like, but we basically want a system where we can go out in the field and survey or sample either troughs or dams where the skeleton weed has been eaten by sheep or kangaroos or the wildlife, and we will have an in-field quick PCR system that allows us to verify in the field the skeleton wheat has been present or absent. And we are looking at other alternatives like feces to be able to do this. So this is still in its early stages, but yeah, very promising technology that could be of use for many, many applications. And that's it. So I want to acknowledge the industry funding scheme, Grain Seeds and Hay, who has been who has funded the project for skeleton wheat research, and everyone involved in the process. Please get in touch if you'd like to discuss. Yeah.
Thanks, Carlos. That's fantastic. We got 2 for the price of 1 there. So that's excellent.